H0, and actually we would reject H0 even with a significance level of 0.05.
It looks all right. Hello dear students! I've just finished a video with some extra exercises on hypothesis tests. In particular, watch out for the graphical representation of the type 1 and type 2 error in exercise 3. This is our last video, however, don't miss out on our last live TA session this Saturday at 5. See you then, enjoy! Great, so exercise 1. The accounts of a corporation show that, on average, account payables are 125.32. So this is an assumption, right? So we have that mu0, okay, it will be clearer later, is 125.32. Okay, an auditor checked a random sample of 16 of these accounts, and it's equal 16, and finds out that the sample mean of the account payables among the accounts checked is 131.78, and the sample standard deviation is $25.41. All right. So assume that the population distribution is normal. Okay, so we will assume that these account payables are normally distributed. Test at the 5% significance level against a two-sided alternative the null hypothesis that the population mean is 125.32, so the mu0. So we have a normally distributed population, right, for which we want to calculate the, we are dealing with the sample mean, right, and the variance is not known, right? So this is case 2 from Chow's. Great. So the H0 that we want to test is that mu is equal to this mu0, which is 125.32. And the alternative hypothesis is instead two-tailed, meaning that the two-sided, so that mu is different from mu0, which is 125.32. Okay, great. So first of all, so we are dealing with the hypothesis test, standard procedure. Step 1, the calculation of the z-score or t-score, and in particular this time is the t-score, because like if the variance of the population is not known, then we only know that this x bar minus, so the sample mean minus mu0 over s, so the sample standard deviation divided by square root of n, this is distributed according to a t-student with n-1 degrees of freedom. So to calculate the t-score, we just plug in the numbers, 131.78 minus 125.32 over 25.41 divided by square root of 16, which is 4. And this leads to a t-score of 1.017. Okay. So step 2, we have the t-score, step 2, right? We want to calculate the p-value. So let me remind you for one more time that the t-score is a score that tells us how extreme the sample is with respect to its sample mean in this case, right? Right, so we found a t-score of 1.017. The p-value tells us, okay, is the probability of having a t-score which is more extreme than the one we found. So to calculate the p-score, I will have to calculate the probability for the t-score to be higher than the one we found, but because it's a two-tailed test, extreme cases are also considered those that are lower than minus 1.017. So the sum of these two areas is the p-value. Okay, the probability of having a t-score more extreme than the one we found. So the p-value in this case is 2 times, because there are two tails, pt 1.017 degrees of freedom n minus 1. Yes, so it's like 15, and lower tail, it's equal false. And the result is 0.325. Okay, so this is the p-value. The p-value of 0.325 is greater than 0.05, so we do not reject. Great. The p-value is a measure of how extreme my t-score is. Here we have that the probability to have a t-score at least as extreme as ours is 32.5%. This is not like too high. Therefore, the H0 is considered plausible. Exercise 2. This is not too different from exercise 1, but I think it's useful to revise the equivalence of the two definitions of the p-value. A process produces cables for the local telephone company. When the process is operating correctly, cable diameter follows a normal distribution with mean 1.6. So we have the diameter of these cables is normally distributed. The variance again is unknown. Great. And under a null hypothesis, it seems, so the mu is equal 1.6. A random sample of 16 pieces of cable found diameters with a sample mean of 1.63. So we've sampled 16 cables, and we have a diameter of an average diameter of 1.63, and the sample standard deviation is S equals 0.08486. Sorry. Okay. Great. Part A. Test at the 10% level against a two-sided alternative, the null hypothesis that the population mean is 1.6 inches. So we have that H0, our null hypothesis, is that mu is equal mu0, 1.6. And the alternative hypothesis is that mu, so it's two-sided, mu is different from mu0. Great, and we have the level of significance is slightly different than usual, so it's 10%. Let's proceed as we always do with step 1, which is calculating this t-score. This is very similar to before, so I'll just plug in the numbers. This is our t-score that depends on the sample mean, sample standard deviation, and square root of the numerosity of our sample, and we get 1.395. Step 2, okay, easy, calculating the p-value. P-value is the probability of our distribution, of our t-score, to be higher than 1.395 or lower than minus 1.395, right? So this red area is equal to, so the p-value is 2 times pt. Well, this time for a change we calculate 2 times the lower tail, right? so we don't have to specify the lower tail equal false. But don't forget the degrees of freedom, which are again same as before, 15. Great. So the resulting p-value is 0.1832267. Okay, I've written too many digits, but okay. So in this case, the p-value is greater than alpha again, which is 0.10. So we do not reject H0. H0 is plausible. Okay. What's more interesting is the second part of this question A. What is the lowest level of significance at which this null hypothesis can be rejected against the two-sided alternative? So our t-score is not very extreme, is not too extreme, but there's a certain threshold. There's a certain threshold here, such that if 1.395 reached that threshold, then it would be considered extreme. And in particular, the green area is 0.10, because this is the alpha of this exercise. What is the lowest level of significance at which this null hypothesis can be rejected against the two-sided alternative? So this is the alternative definition of p-value. We've seen two definitions. So the first one, well, you can order them however you want. The p-value is the probability of having a t-score just as extreme or more than the t-score we got, or the p-value is the lowest level of significance at which the null hypothesis is rejected. So in this case, the lowest level of the lowest level alpha at which H0 is rejected is exactly equal to the p-value. So whenever alpha is greater than 0.1846. Okay, so because like if, for example, alpha is equal to 0.185, then the p-value will be lower than alpha, and therefore we reject. Okay, so very important alternative definition, or the main definition that you've seen of p-value is the lowest level of alpha. If alpha is equal to that level, then the null hypothesis is rejected, right? And this happens exactly when alpha is slightly higher than the p-value, right? Okay, second part, it's rather easy, and it asks us test at the 10% levels, so same significance against a two-sided alternative, the null hypothesis that the population mean is 1.6 inches if the standard deviation of the process is known to be sigma equals 0.06. So same as before, but this time we do have the value for the standard deviation, which is 0.06. So instead of a t-score, this is case 1 from Chaus. Okay, instead of a t-score, we have a z-score in this case, and this z-score is x bar minus mu 0 over sigma over square root of n. Now, I won't bore you with the calculations, but this is 2. The p-value corresponding to 2 is 2 times p norm Okay, this time we'll calculate the upper tail force, which is equal to 0.0455. So in this case, we would, as the p-value is lower than 0.10, we would reject H0. And actually, we would reject H0 even with a significance level of 0.05. Okay, exercise 3. I think that this exercise is very useful in gaining some extra intuitions on type 1 and type 2 error. So, let's read it. Supporters claim that a new windmill can generate an average of at least 800 kilowatts of power per day. Daily power generation for the windmill is assumed to be normally distributed with a standard deviation of 120 kilowatts. I'm not sure that this is the way it's pronounced, but we don't care. So the daily production is assumed to be normally distributed with a standard deviation of 120, and under some assumption, this like null hypothesis, so our assumption mu 0 it's equal 800. A random sample of n equal 100 days is taken to test this claim against the alternative hypothesis that the true mean is less than 800 kilowatts. So the difficulty of this exercise is clearly not to identify the null hypothesis, as the null hypothesis is that the mean production is 800, and the alternative hypothesis is that the mean production is lower than this mu 0, so is lower than 800. However, there's a twist. So it's different than usual. The claim will not be rejected if the sample mean is 776 kilowatts or more, and rejected otherwise. So this time we are not given for a certain confidence or significance. We don't have to come up with a rejection region. We don't have to come up with a p-value, but we are given the rejection region. So a statistician has already worked on this and has found that the claim, so this H0 will not be rejected if the sample mean is greater than 776. So this means that we are given with the rejection region, the critical region. So we reject H0 if the sample mean is lower than 776. So a bit different than what we're used to have. Let's see the questions. What is the probability of a type 1 error using the decision rule? If the population is in fact 800 per day. So, well, of course, the type 1 error is the probability for the sample mean, in this case, to be inside the rejection region, assuming that H0 is true. Okay, and in particular, as the rejection region in this case is for the sample mean to be lower than 776, we want to calculate the probability for this to happen when mu is equal to mu 0, that is 800. Okay, great. So how do we do this? Well, under H0, we know that, so we don't know the significance. So usually the type 1 error is set to alpha, and usually alpha is 0.05. However, we don't know the significance of this particular test. So let's calculate this. So, but we know the rejection region, and from that we can calculate the significance of the test. Under H0, so under H0, X bar is the sample mean of a normally distributed population, so it's going to be normally distributed with mean 800 and variance 120 square over the number of the samples, right? So we will call A this value. The probability for x bar to be lower than 776, knowing that mu, well, it's equal to 800, it's equal to, this is rather easy, so P norm, so it's just like the probability of a normal distribution to be lower than 776, specifying its mean and a standard deviation. The square root of 120 squared divided by 100 is 12, right? Trust me with the calculations, 0.0227513. Okay, so this is the type 1 error given this critical region. Let's move on to part B. What is the probability B of a type 2 error using this decision rule if the population mean is in fact 740 per day? So now we want the type 2 error. Okay, so let's call, the type 1 error, we've always called it alpha, so let's stick to alpha and beta for the type 2 error. So the type 2 error is the probability for x not to be in the critical region, okay? So if the alternative hypothesis is true instead, right? So all the errors are mistakes that we do. And so, if x bar is not in the critical region, then we do not reject, but we should, because the alternative is, hypothesis is true instead and not the null hypothesis. So how do we calculate this? This is done in a very similar way. So under the hypothesis, the alternative hypothesis that mu is equal to 740, x bar is normally distributed, but with a different mean than before, so 740, and but the same standard deviation, right? Variance. So beta, which will be the probability for x bar to be not in the rejection region, so greater or equal 776, given that mu is equal to 740, then it's just the probability for a normal distribution to be greater than 776, with the mean 760 and standard deviation 12, right? So the probability for the standard normal to be greater, so don't forget the lower tail, equal false. Great. And this is equal to 0.001345. Okay, so this is our, where is it? Alpha. And this is our beta. Great. So, so far, everything hopefully makes sense. Now I just wanna plot, okay, a simple graph, okay, to understand what is happening and how we can graphically see these alpha and beta. So let me see. We have a axis here, okay, and this is x bar. So x bar is the sample mean. The sample mean has a different distribution depending on what mu is. So, for example, if mu is equal to 800, so let me, okay, it seems all right. So if mu it's equal to 800, then, so this will be the distribution of x bar under, under the null hypothesis that mu is equal to 800. If we have considered an alternative hypothesis that we will plot in purple, okay, it's not important, but so the the alternative hypothesis that the mean is instead 740, so lower. Okay. 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 Yeah. All right, it's not perfect, but good enough. So this is the distribution of x bar under H, the alternative hypothesis that mu is equal to 740. Okay, so let me put 740 here. Great. So another element that we can add to the to this representation is the critical region. So the critical region is 776. So let's say that here is 776. Okay, so slightly closer to 800, and the critical region is whatever lays below 776. So this is the critical region, which is x bar lower than 776. Great. So from this plot, it should be easy to see where the type 1 error and the type 2 error is. So the probability to be in the critical region under H0, okay, so we commit a mistake, and is the type 1 error. So is the probability of being in this region, okay, so red area, type 1 error, and it's called alpha. Instead, the probability of being, so I'll use the green now, the probability under H1 of not being in the critical region is the type B error. So it's this tail here, right? So this is type 2 error, which we always call beta, right? So so this part is great. It's a nice plot, kind of, but it's important to understand what is happening, and I've done this in particular to solve the next two questions of this exercise. So let's read it. Suppose that the same decision rule is used, okay? So the decision rule is represented by the critical region, but with a sample of 200 days rather than 100 days, okay? So we have in part C, we have a critical region unchanged, so the red critical region, right, is not changed, but more days, so n increases, okay? And the question is, would the value of alpha be larger than, smaller than, or the same as that found in part A? Would the value of beta be larger than, smaller than, or the same as that found in part B? So we are interested in understanding where alpha and beta, so if they increase or they decrease. And so to answer this question, we don't need to do any calculations. You can do the calculations to double check. However, just know that x bar is in all cases distributed according to a normal distribution with variance sigma over square root of n, right? So if n increases, if we increase n, the effect on this distribution is that they become pickier. So for example, the distribution under H0 could become like this, pickier, because the variance is decreased, right? The variance is decreased, and therefore this will lead to distributions with thinner tails. Okay. So I don't know. Yeah, you can see that the tail here is thinner than the tail before, and therefore the type 1 error decreases. So this is the type 1 error now, right? Which is much lower than the type 1 error before, right? So let me delete this because I don't want to ruin our plot. However, I hope you get that we got like thinner tails, and therefore alpha decreases, right? And the same is true for beta, okay? Because if n is increased, then the distribution of h bar under h1 under the alternative hypothesis is pickier as well. So again, we have something like this, okay? And you can see that this would be the type 2 beta, which is lower than the beta we had before, right? Okay, so alpha decreases, but also beta decreases. And this is the answer to this part C. Let's look at part D. Suppose now that a sample of 100 observations was taken. So now n is back to 100. So this is the situation at the moment. But that the decision rule was changed. So we changed the critical region so that the claim would not be rejected if the sample was at least 765. So this time the critical region is changed. So we only reject if the sample mean is lower than 765, right? So in case D, we have that the critical region shifts left. Okay, it shifted to the left. The n is the same, so n is 100. What happens to alpha and beta? This is maybe easier to check. So this was alpha before, right? Alpha becomes much smaller, decreases. So alpha decreases. However, for beta is the other way around. So the green part was beta, right? But this time beta is this area here. So instead beta increases. Okay, so the only way we have to reduce both type 1 and type 2 error is to have a sample with more samples. So yeah, to increase the numerosity of our sample. And I hope that this graphical representation of the distribution of x bar under h0 and under h1 can help you to understand all the different elements we have in our hypothesis test. This is one of the exercises in your exercise sheet number 10. And this is exercise exercise 9 from sheet 10. Okay. I've been asked to solve this exercise, but I think it's a particularly useful and it's a useful and complete exercise, so I decided to add the solution to this video. Okay, so two blood pressure meters, A and B, gave the following measurements on a sample of 16 individuals. All right, so we have sample type A and type B. Okay, we'll call, because we are used to do this, the first sample X and the second sample Y. So I've done all the calculations in RStudio. So I'll just report the functions that we can use to solve this exercise. You know, there are a lot of calculations, so it's easier, faster and safer to carry them over in RStudio. So to define we can define two vectors, writing X equal to C for concatenate, remember, and we concatenate all the different values in the first measurement, 56, 87 and 86, and the second sample with 66, 74, 82, 77, lot of samples, 58, 79, 80. Great. So the first question is there a meaningful difference between the mean of measurements of the two devices? So first of all, let's calculate some statistics of these two samples that will be useful, or that we will need for carrying over this hypothesis test. So X bar, that is the mean of the first sample, can be obtained once you've defined the two vectors X and Y by mean of X, and it's 81.625, I believe. And X squared, this is the sample variance, you can compute it with the function var, and it's 145.6964. Same thing we can do the same thing for Y. Okay, so the mean for Y is 75.8875, and the sample variance, okay, is 102.125. Great. And X, number of samples in the first sample, okay, is 8, and so is in the second one. And D, that is the difference between sample means, so X bar minus Y bar, it's equal to 5.75. So our null hypothesis is is this distance between the two means equal to D0 is 0? Is it 0 or is it not 0? So D different from D0. Okay, recall that D is the population mean of X minus the population mean of Y. Okay, so I hope you recognize it. You recognize this case at this point. Is the case 5 from Chaus. Okay, we have two populations. Two samples. The samples are from two different populations, and so we don't know the variance, but we have the sample variances. We want to understand whether the population means differ. We will assume, okay, so it's not written in the exercise, however, this is the only case we can treat, right? So there's a little, small simplifying assumption. Assume that the variance for X is the same as the variance, so the standard deviation of the first population is the same as in the second, even though we don't know them. So we will call this, I don't know, sigma. Right, so same as usual. Step 1, t-score. So the t-score is given by d bar minus d0 over square root of, do you remember the pool variance? So a bit annoying calculation, but we can do it. And y. Right, so the t-score will be d bar minus d0 divided by the square root of this guy here. So we will call this, okay, k, right, because like we will need this later, so it's easier to define it. So the pooled variance is defined as nx minus 1 times sx square, right, plus ny minus 1 times ny square, divided by nx plus ny minus 2. Great. So if you trust me with the calculation, this is 123.9107. Okay, so this value that we have found divided by nx plus same value divided by ny, we call that nx is equal to ny, which is 8, and we take the square root of that, this is equal to 5.565759. Step 2. So we have a t-score that we have calculated. Okay, sorry, I forgot to complete this. So d bar, which is 5.75 divided by k, as this is equal to 0, right, gives us 1.033102. Great. So next step to decide on the null hypothesis is to calculate the p-value. So step 2, right, will be calculating the p-value, but here nothing changes, right, than the other cases. So the p-value will be 2 times, as usual, two-tailed, so 2 times pt of 1.0331, okay, too many digits, but never mind, degrees of freedom, nx plus ny minus 2, so this will be 14 lower tail, equal false. And this is equal to 0.3190, okay? So as the p-value is higher than the level of significance 0.05, then H0 is plausible. So there is no significant difference between the sample mean of x and the sample mean of y. So we can't reject the null hypothesis that in fact these two population means are the same. So this is the easy part, well, the less challenging part of the exercise. What's a bit trickier is the second part. Compute the probability of the error of type 2 for the alternative hypothesis, blah blah blah. Okay, so you know that when we are asked to compute the type 2 error, we do have to calculate the critical region, right? So the critical region, so we have, I'll do a tiny plot here. So we have found that our t-score was, okay, this is not really, okay. Our t-score is 1.033, right? And minus 1.033, as usual, the p-value is here, and we found that the p-value was 0.3190. What is the critical region? Well, is the region in green such that the probability, so that contains the 5% more extreme cases. So we have that those two tails summed up have to give 0.05, and that will be our critical region. So the critical region alpha is equal to 0.05, so we can write this right away. 0.05, it's equal to, well, we reject if the t-score is lower than minus t alpha over 2. Alpha is 5%, right? Or we reject if the t-score is greater than t alpha over 2. Okay? So it's easy to calculate this t alpha. So t alpha over 2, so 0.025 is the quantile of a student distribution with, well, evaluated at 0.025, degrees of freedom 14, and lower tail equal to true. And this is, let me double check because I didn't write this down. Okay. Okay, this is 2.145, right? So the critical region, R alpha, corresponds to the values where the t-score is lower than minus 2.145 or the t-score is greater than 2.145. Okay, this is the critical region in terms of the t-score. However, you know that many times, well, most times, we really need the critical region in terms of our sample mean, or in this case, in terms of our sample difference between here. So the t-score is d bar divided by k. So in this case, so the critical region is, so the t-score is d bar divided by k. Well, we can write this here, right? T-score, it's equal to d bar divided by k. So if we express the critical region in terms of d bar, we'll have that we reject, so we are in the rejection region if, let me just recalculate this, okay, d bar is lower than minus 11.94 or d bar is greater than minus 11.9 plus 11.94. Great. Right, so this is our critical region. Why do we need this? We need it to the critical region to answer to the second question B. Compute the probability of type error. So as usual, our type 2 error is beta, is the probability of not being in the rejection region. Okay, so for d bar to be between minus 11.94 and 11.94, given that the real distance is 3. Okay, so we'll do this case, and the other case is very similar. The other case is like very similar. Okay, so many times, so when we have to calculate the type error, for example, for the case 1 for Chaus, we know, like here, we have the sample mean. Usually, we have the sample mean, and we know the distribution of the sample mean under the alternative hypothesis. In this case, we kind of like don't know the distribution like a d bar under the null hypothesis, but it's easy to retrieve a well-known distribution if we let's say standardize this distribution. So we don't know this one. However, with a simple calculation, we can write that this is equal to the probability, okay, for minus 11.94 minus d over k to be lower or equal than d bar minus d over k to be lower or equal than 11.9494 minus d over k, d equal 3. So where d is equal 3 and k is the number that we have calculated before here, right? So beta is equal to the probability for this guy here to be between minus 2.684 and 1.606. And this is a pivotal quantity, okay? So for the difference between two, so when we're dealing with the difference between population means, these d bar that we can call, I don't know, sample difference, the sample difference, okay, or the difference between the two sample means, minus the true distance divided by this guy here, that doesn't change, is a t-student with an x plus n y minus 2 degrees of freedom. So this is an x plus n y minus 2 degrees of freedom. And this is very easy to compute with r, right? As this is, so pt 1.606 with degrees of freedom equal 14 minus pt minus 2.684 with degrees of freedom equal 14. Okay, and this difference done, it's equal to 0.9258. Okay, great. So this is well, not too difficult. However, you do have to gather all the different knowledge you have about well, first the p-value, then definitely be able to calculate the critical region, and I'm sure that you're able to do this, right? And the critical region for t-score, for the t-score, and the critical region for d-bar. However, the difference with respect to other cases is that we can't calculate the type 2 error just directly from here, but we have to standardize first. And then remember that for this case of the Chows, we have that this is a pivotal quantity, so it's a t-score, and therefore after we've standardized, we have that kind of distribution for which we can calculate probabilities. So 0.9258, rather high, is the type 2 error, the probability of not rejecting if the alternative hypothesis is not 0 but 3, right? So you can try and do the same with d equal minus 3, but it's very similar. The standardized critical region will change, so this is the only part that changes, right? And probably we will have inverted, so it's going to be minus 1.6 and plus 2.68, but the probability will be the same. Okay.
Of 0.05.
It looks alright. Hello dear troppa scena. And in particular, watch out for the graphical representation of type 1 and type 2 error in exercise 3. This is the last video, however. Okay. I've just finished a video with some extra exercises on ipothesis. Hello dear student! Perché non mi segui? Perché? Braccio mecatronico!